Hi, my name is Dave Farley and welcome to the Engineering Room. If you haven't been here before, do hit subscribe, and if you enjoy the content today, hit like as well. Do join in the conversation too and let us know your thoughts and ideas in the comments below. The Engineering Room is an occasional series and is meant as an addition to the more usual content on the Continuous Delivery channel. These are longer form conversations with some influential and thoughtful people from our industry. Today, I'm joined by my friend Kevlin Henney. I first came across Kevlin at a conference in Australia many years ago, although we're both English. He gave several talks at that conference, including a keynote, which was funny, unexpected, educational, and brilliantly well presented. Over the years, I've come to expect nothing less than that from Kevlin. That's his norm. As I started talking more frequently at conferences, our paths crossed more often and we became friends. Kevlin is an independent software development consultant, trainer, speaker, and writer. The people who work with Kevlin always speak very highly of his services. He's witty, nerdy, sorry, Kevlin, and smart. He also has a Google unique name. Try it, you'll only get Kevlin. And rather strangely, among the cognoscenti, if you ever see an obvious public software failure, a screen in an airport showing a command line or an advert in a store showing the blue screen of death, it's called a Kevlin Henney. But no doubt we'll get to that. Welcome, Kevlin. Did I miss anything important?
No, thank you very much, Dave. That's the perfect introduction. I'm going to copy and paste that. And use that
Great, thanks. Well, I've been looking forward to this talk for a little while. The last time we met was in Copenhagen at a GoTo conference, and my wife and family took the mickey out of me for the rest of the conference because you and I, every time we crossed, we spent all of the time talking rapidly in great detail because we hadn't seen each other for a while.
That was what, but the funny thing is the way that coincidences worked out is that pretty much the moment I arrived in the hotel, you and family were there, and I bumped into everybody, including your son and daughter-in-law, at the airport when I left. It's just like, paths crossed quite a lot there. So yeah, plenty to talk about, plenty to catch up on.
Cool. So let's start with that production failure being called a Kevlin Henney. I think I know the answer to this, but tell us how that happens.
Yeah, well, so it's one of the things. I guess it's, if you're in software, if there's something you're really into, you become sensitive to things. You start spotting things, and I was always fascinated by the fact that see occasional failures in places. You occasionally see a cache machine booting up and stuff like that. You kind of notice this stuff. It makes you ask questions about it. But then we hit the kind of like cameras on phones era. And at that point, suddenly it's like everywhere I'm walking, I have a camera, and the amount of software that we actually have everywhere is huge. So I'm starting to take pictures of these things. I'm also taking screenshots whenever something crashes, particularly if it's losing my work. I'll take a screenshot and hold on to that because I think it's fascinating, because it's kind of like, okay, it's often frustrating, but it's fascinating. It's just like, okay, this is my space. I'm in software. Collectively, we somehow created this, and I'm fond of noting that we, as in software development, are the largest creators of a kind of guerrilla installation art on the planet. Nobody else comes close, But I used to kind of collect these, and occasionally I kind of put them in talks, or when running a workshop or training course, I kind of have them on my screen, just like as a screensaver in the breaks. Always causes conversation, and I always pointed out, oh, this is really interesting, because in failure, when something fails, you learn something about how it was constructed. It's kind of like at that moment you lose all the encapsulation. You're presented with something when it works that is beautiful and pristine and pixel perfect, and it offers some kind of user experience. And maybe you can guess the technology, but most of the time you can't. And then it's like you drop something on the floor and it fractures, and it's just like, oh, look, this bit's made of C#, or they're using that as part of their stack, or I'm pretty sure that's out of support now, or whatever it is. You see it loses its encapsulation. It loses that kind of like surface, and we see the insides. And if it doesn't tell us directly how it was built, it invites questions. It makes you go, oh, I wonder how did this arise? Did they forget to put a try block here? Did they forget, how did this exception escape to the user? But I just did that kind of as a point of fun, as a point of personal interest, and a point of showing people. And then people started sending me these things by email, and then we hit social media era. People start sharing it more directly, and then it's Twitter, and people are just like posting it and just atting me. Then I start retweeting it, and then that's where it acquired its name, and it actually made its way into Urban Dictionary, the Register, and a bunch of other things. So yeah, it's just one of those things. And the incidental side effect is it's interesting. I find it's still fascinating. I think there's a kind of a humor to it, as well as a serious point to be made in all of these things. But it also ends up being an accidental service, because sometimes you're talking about rail services and train stations and things like that, and often people will at the train company as well, wherever they are in the world. And you can tell what the customer service is like, because often they'll go, instantly jump on that and say, which station was this? I'm really sorry this happened. Or there'll be just silence. And so you can kind of tell, you get a sense of the customer experience as well as the failure experience.
That's brilliant. So kind of the archaeology of failure.
Yeah, that's exactly it. Yeah.
That's great. I often think that I know we don't think too much about the failure routes so often. Yeah. There's one of my favorite quotable bits of research was a Usenix survey from a few years ago that looked into the cause of production failures, and something like 60% of production failures are in the error handling path. The most common line of code in the event of a production failure is a comment saying should do some exception handling here.
yeah and I think that's a really interesting, because that one, if it's the one I'm thinking of, that was 2014 paper. Yeah. But there's probably been others. But I think I first came across that was somebody did a study, the late 90s, early 2000s. Unfortunately, I can't cite it. I can't remember who it was. But they did an analysis of failures in the Linux kernel, and they said it's mostly on the error paths. Yeah, the dark alleyways that just don't get explored and tested anywhere near as often. Happy Day works out fine, but these little edge cases, something goes wrong, and then either it was just like this was to do, or somebody had an idea of like, it should be something like this, but it was never really tested. And it kind of got marginalized in their memory, and now control flow is wandering down this dark path that's been untested to deal with a really bad situation, and the situation gets worse. It's one of those things, and that seems to be a recurring theme, that these edge cases, it's kind of they when you're at the edge case, it's not an edge case anymore. It's your world. Yeah.
It's one of the things. That I did some research for my book into the kind of history of software engineering, and of course Margaret Hamilton was a huge heroine in that field in the early days of that. And one of the things that I loved that she went on about was talking about the importance of the systems that she was working on, the flight control systems for the Apollo missions, being man-rated. And so the reason why she coined the term software engineering was because they were spending all of their time worrying about how things could go wrong, like engineers do. If you don't build a bridge and you only worry about the happy days, you worry about when there's a storm or when the load's too heavy, or all of those kinds of things too. And we need to be thinking the same for building serious software systems.
Yeah, I think a lot of the stories around Margaret Hamilton are absolutely brilliant. I mean, the fact that there's one where she brought her daughter into work, one day, and daughter recreated an error or created an error condition just by messing about with it, put it into a state. It's just like cats and children. And other cases where these the kind of the classic. Certain machismo associated with the fact that at that point all astronauts would have been Air Force pilots, and the culture and image that went with that is like, these are highly trained people, and they won't make mistakes like that, and then promptly one of them does, and it's just like they go back to her, it's like, let's do that, let's put that failure happen in there, because it doesn't matter that they're highly trained, the operative word in that sentence is people. It's highly trained gets you so far, but you're still ultimately human. And I think that and one of the other points that I read that Margaret Hamilton talked about is she was trying to really get a seat at the table, as it were, because certainly at that era, this whole idea that software could form a viable, meaningful first-class component of a system, as opposed to just a secondary component, was completely a foreign concept. And there were even astronauts saying, well, we don't think we're going to need software. We don't actually need software to land on the moon. And it's to anybody who's either studied the physics of it or is familiar with any of the modern stuff around this, it's just like, yeah, you can't just fly by the seat of your pants and that's going to work out. You need this stuff. And so she wanted that seat at the table. And she, engineering was the term that she chose. We got to treat this in that sense. It's up there with all the others, because this is not just icing on the cake. This is not just a glorified slide rule. There's something deeper and more fundamental here. We're talking about control systems and the data that is genuinely life critical. This is not just a slide rule. This is beyond that. It's the idea of it's not just a calculator, whereas I think many people thought of this as just an extension of the calculator.
Yes. Yeah, absolutely. Brilliant woman and a real pioneer in our field, I think.
Yeah, definitely. But I think that's one of the things that I found with because one of the other things that is, we had this term engineering that kind of took off from different points, and I've seen it misattributed. So I've seen things where people said, "Oh, the NATO sponsored 1968 software engineering conference was the beginning, coined the term." It's like, no. They used the term because it was already around. Margaret Hamilton initiated that. I think I stumbled across a bit in communications of the ACM that it was used as a term in 1966 in there. And in other words, there's a kind of a lineage. So by the time the conference came around, this term was currency, and it existed. And that was trying and say, well, what does this look like if it's for software? But I love some of the I know you looked at it for your book, and I did a whole load of talks in 2018 because it was 50 years on. So I thought I did a series talk 1968. I thought, you know what, I'm going to actually go and read end to end the whole proceedings, and also look at the 1969 one as well. But do that, and I did that a couple of years beforehand, and I found it absolutely fascinating because one, it's an amazing historical document, capturing some really interesting insights. But also there was a real sense there. One of the things is, some of it is incredibly dated, because it does date because they're talking about technical constraints and concepts from the 60s. But at other times, it's just like, it's not that you agreed on everything, but all of the ideas that we now debate and push forward were present. They were there. They arrived. And problems that those people were facing in building real systems, even though the computers that they were building them for are all in museums now. It's one of the things that got me interested in kind of talking about engineering in my book and stuff was that I think that we discard some of those really durable ideas too readily. That there are things at the heart of our profession. I think the most important things about our profession that haven't changed since the 1960s. And as you said, I had hairs standing up on the back of my neck when I was reading stuff by Alan Perlis, describing in language that sounded quite dated in many words. His choice of words sounded like somebody from the 1960s, but nevertheless, he was expressing ideas that still too many software development teams don't even think about doing, to their detriment. Crazy. And I think there's some really interesting things in there about that a lot was up for discussion, but also sometimes some of the discussions were that they're talking like old hands. They're talking about, it's been going on for 10 years, like it's a really bad thing in here. And so the fascinating thing about doing this talk 50 years later is just like, well, they thought it was old hat when they did it 10 years in. We're half a century on. How are we doing here? And there's some really, really interesting things. So from my perspective, one of the things I'm very interested in is testing, and interestingly, before reading that, I had kind of presumed that unit testing as a term, I kind of dated that to the 1970s. I'd found, I hadn't really pursued it back in time, but 1970s was what I had in my mind based on what I'd read, and I thought, that would be terminology. But I look at the software engineering, proceedings, and there it is. The term unit testing is there without qualification or definition. In other words, it's not presented as, here is a new idea. It's presented as, oh, okay.
Assume everybody knows about it.
Referring to it. Yeah. And it was really interesting, just looking at certain ideas like that, as well as some other historical kind of foreshadowings. So a number of years ago, I was quite heavily involved in the patents community. There are a number of elements in the patents community and patents thinking, which I think have been hugely neglected for me. One of the real turn-ons was the whole idea of really understanding this is a pattern. It's not a principle. It is not a universal. Here is an idea, and you know what? Sometimes this works in some cases and not in others, and here's why. And people often miss that. They kind of latched onto the surface, as it were, but not really understood the depth. And for me, the huge influence was the trade-offs. Understand the trade-offs. Here is just like, here we go. Here is why this works well here, but doesn't over here. The context dependence of the idea was absolutely huge. So rather than talking about software from the perspective of mathematics, which is timeless and universal and all the rest of it, here was something that was hugely dependent on, well, I can't tell you what's right. Somebody says, is this the right way or is this wrong? It's just like, well, it's going to be that it depends. And that's not because I'm being a consultant. It's because genuinely there are about 3 or 4 different ways of doing this. You've got to show me the landscape. You've got to show me the landscape that you're going to put this into. My answer will be different if you're dealing with a legacy system, perhaps, than with a modern system. It'll vary from language to language, depending on certain elements. But there might be broader ideas that are still stable. But there are, if you say, oh, this is in a multi-threaded environment, then I might retract my previous answer and go, okay, actually, we're going to take a different path here. And it's the contextuality and understanding the trade-offs. For me, that was really exciting. Now, we tend to, for a lot of people, they tend to credit the Gang of Four, Gamma, Helm, Johnson, Flaccides with the patent stuff. Now, certainly that initially turned me on, but even before the book was published, I'd heard about this stuff. But it was this other stuff that was going on. It's like, this comes from architecture. This doesn't come from software. This comes from architecture. And Christopher Alexander kind of originated this idea. And it's this whole idea of, he was really big on the idea of, you've got to have an empirical design. In other words, he was trying to move building architecture away from fashion, which is something I think we get plagued with in software as well. He was trying to say, well, look, there's an empirical solution to this. Does it work? Here are the qualities that make something work. Have you defined your problem? Does this solve the problem of living, or whatever context he was looking at? And he was very clear. He used the language of empiricism all the way through. This is not to say there were no artistic qualities to it, but I was always fascinated. And his writing style, again, it catches the time. It's 1970. So I started reading all the Christopher Alexander stuff. And then you eventually hit another book by Christopher Alexander, Notes on the Synthesis of Form, which was published in 1964. And I had a vague awareness that this had a big influence on a lot of disciplines at the time. But reading the 1968 NATO software engineering proceedings was fascinating, because they kept referring to Christopher Alexander, but this predates his patents work. It was all synthesis to form, about how he thought about design in terms of balance and trade-offs and sort of isolating systems of change from one another and all the rest of it. Hugely influential, but kind of forgotten. That kind of got buried there. So there's this little capsule into the kind of like the zeitgeist of the 60s and design thinking and all this kind of stuff. Conway gets mentioned, Melvin Conway, and this influence on architecture of like, the way that your people communicate is going to have a huge exert a force on the structure that you build. How you communicate is going to influence that, because this is not maths. This is we're creating a thing, and our choice of creation is going to be influenced by how we talk to one another. And there again, this gets multiple references throughout the software engineering proceedings, which I found.
And I think that's deeply entwined in terms embedded really in what engineering really means. I must confess, I love maths. I actively enjoy maths, and sometimes solve mathematical problems as a hobby, but I don't think that what we do is maths. It appeals to mathematical thinkers, but one of the differences between engineering and maths is that engineering has that pragmatic bent. If you could simulate an aeroplane, the design of an aeroplane, and wholly do that, in a simulated form, and just build the aeroplane and then take passengers, people would do that, but they don't. They do that, and then they go flying. And certainly, if you're Boeing, I don't know whether they still do it, but certainly for a very long time, the engineers that built the aeroplane were amongst the first passengers after the test pilot went up to go for a ride in the aeroplane that they designed. So there's this thing of trying stuff out, and I think that's one of the principles that I get a little frustrated sometimes with people talking about the mathematical nature of programming. It's interesting, it's fascinating. I like thinking in those sorts of terms, but I don't think that's enough, because I think it's usually harder to be able to write something that's a provable system than it is to write the system in the first place, and so it's almost more error prone. So it's a complex problem. I was just listening to the radio today about. Actually, I was listening to a podcast from New Scientist, and they were saying they've just rejected one of the supposedly quantum computing proof encryption algorithms because somebody managed to break it on their laptop.
Oops.
And you'd think that'd be a fairly mathematical kind of area of software. So when we're building flight control systems or car control systems, or even your stock control systems, there's still room for all those human errors and mistakes. And Margaret Hamilton's little girl to come in and screw it up in new and interesting ways.
And I think that's a really important thing, because it's because this kind of whole point about kind of perspectives of when we look at things, how do we reason about them, and that it's a distinction I made a number of years ago, so that software, there are lots of elements of it that are mathematical but are not the same as but not mathematics. In other words, there's a distinction there. So engineering is not mathematics, but it is mathematical. In other words, it draws very heavily, it uses it as a tool, and that tool can also give us further insights, but they are not an equivalence. There's not, and that's a really important distinction. And that idea of yes, but when I throw it, does it stick? That kind of stuff is the real thing. When we actually, sure, this works in the simulation, but it's this. It's like let's take it back to the 80s. Aliens, being asked, how many combat drops have you done? Yeah, and then we get one answer. It's like, and then follows on simulated, and it's just like, right, okay, there's a big distinction here. You've actually, this is your first time properly in the field, is a big distinction. So in other words, there's that whole kind of idea of like the math, and I think for software, the term, there's a lot of mathematics that is in bits. There are things that are genuine mathematics. There's a lot that is mathematical, but the better way of looking at it is formal. Now, I don't want to get that wrapped up with formal methods, because that's clearly an important subset, but it's formalized. In other words, there's elements, and that's something I've always found fascinating, is that you got the human element, which is definitely hugely informal, sloppy. We are not formalized creatures. We're very, very associative. And then what developers have to do is bridge the gap between this incredibly sloppy world that somehow has form and shape, but is not necessarily rigid and prescriptive and with well-defined boundaries. And then you kind of shift into the world of programs, which have exactly the opposite nature. They are highly formalized. It's a programming language is a formal structure. There's no kind of like, well, maybe today I'll compile it, or maybe you don't. And if it looks like that, you have a problem. But and what you've got to try and do is build a system for the kind of the soft, squishy thinking and soft, squishy beings out of stuff that is really quite different. And yes, the nature of these two, bringing them together, I think that for me, that's one of the things I find fascinating, but it's probably also for many people, without them realizing, is what's interesting about software development is there is the rewarding aspect of some things that are solved and elegant, and it's just like, that's done. But then there's the other element of like, and how does it fit with the world, which is also quite exciting. And also the discoveries that you make is just like, well, I thought this was a really good abstraction, but now I truly understand what's being built. I don't think that's the right abstraction. That doesn't mean it's a bad abstraction. It's just not the right abstraction for this system. It's just now I understand how it's evolving through time and the kind of the nature of changes that the client wants from it, or the things we've discovered from sprint to sprint. It's just like, oh, okay, I keep touching this, keep changing it with that optimism. Oh, I'll get it right this time. But actually, maybe I'm learning something deeper. The fact that this is not the idea that I thought it was, and I need a different point of view. And that's not a side effect or an accident. That's the nature of the game. It's this exercise. It's this continual exercise in learning, in which we enhance our understanding of the problem that we're trying to address, and the nature of our solution that we're trying to apply to it. And it seems to, that's one of the things that I've very, very strongly come to believe, that that's a complete cornerstone of our discipline. And we optimize to be able to maintain our ability to make changes when we learn new stuff. So I refer to it as this kind of one of the ways of kind of pragmatically, informally adopting the philosophy of science to software. So I want to consciously start out assuming that I'm going to make a mistake and I'm going to be wrong, and then I'm going to look at ways in which I can falsify my guesses along the way. And that's a much stronger way of learning than assuming that my design's perfect and it's going to be right, and I'm never going to have to correct it again. I've found the one true way, I'm always reminded, there's this is years ago, but I had a client where I'd become over successive visits, I'd become familiar with the nature of their system and what they were doing. And they one day asked me, well, we'd love you to design this kind of like subsystem, and it's got these performance constraints and stuff like that. And we've got the suggestion for the basic idea of the design. And I kind of said, I don't think the memory manager is going to like that. I don't think that's going to work. I don't think it's going to meet the performance requirements that you need. I think there's going to be issues with it. And I made a suggestion, and they said, are you sure? And I said, well, I think this is going to work better. I think this will work better with memory allocation on this platform. I think that for the, you're dealing with peak, they basically wanted to deal with peak demand in some way. We can't handle all the data, but what we need to do is spool it off so we can handle it later. And I said, I think the way I'm proposing will work this way. And then I tossed in another idea, because I'm not really happy until I've got three ideas. So they gave me one. I had a preferred one. I didn't think theirs would work. I had a preferred one, and and then I had a third one, and I thought the third one was okay. I thought it was better than their suggestion, but I didn't think it was great. And they gave me a couple of days. They fed me coffee. Gave me a meeting room, all the rest of it. But my favorite thing is one of the guys came in one day, first or second day, and he came in and he saw I had an idea on my screen. I had code. There were curly brackets happening, and he said, "Oh, we didn't expect you to code." And it's just I kind of looked at it. It was just like, well, how do you think I was going to do this? Sit here and make it for 3 days, and come up with the pure design, just moment of light when it's like, no, I have designed it. I am the architect. This is the matrix or whatever.
Here is the word.
Here is the solution. And it's just like, no, I'm trying each one of these out. I want to see what it feels like in code. And also I'm going to do some basic performance analysis. Nothing too big, just to get a kind of order of magnitude feel for this stuff. And I wrote it up. And the funny thing is, I wrote it up, and it's only in hindsight that I realized I'd written it up like an experimental report. Here's the situation. Here's what we've got. Here's the various proposals. Here's how we've run it. And here's the results and recommendations for future work. But what I found is that I was right and I was wrong. I was right. Their approach wouldn't meet their requirements. I was also right that my preferred approach would meet their requirements. But I was wrong in that my kind of like third throwaway option, that was outstanding. It was way ahead of me, and I would not have known that by meditating upon it. That had to be made real. That had to be brought into the world. And to actually, you also have to kind of mess about with it. In other words, the very act of, and you mentioned kind of like solving mathematical problems for fun. And that's one of those interesting things, is that I'm guilty of having done similar things in the past. And it's kind of fun. But the thing is, until you've done it, you don't know how you're going to do it. You've got some ideas and you're going to crack away at it. And in that sense, there is a sort of a creativity. It's mathematics is not necessarily empirical, but it is certainly creative. I'm going to try this. Oh, I don't work. Oh, what about this one? Oh, what about this? You've got that. And software just pushes it that little bit further to bring it into the world and say, well, but how does that work in the world as opposed to in abstract space? And that is a really important, and that idea, I think it's a really interesting one, because what we're doing is we're bringing together the idea of problem solving and creativity, but with something that somebody else is going to experience and they're going to work with it. That somebody else is either going to be another developer experiencing the code, or it's going to be an end user experiencing what is this system like. And so there's a kind of a feedback. You don't necessarily get that quite the same from something that is mathematical. There's a kind of a sense there of, is this appropriate for the world that we want, as opposed to, this is fine, it's a nice idea, but it's a case of like, what is its context? I can draw you a picture of a house, and I could ask you, is this a good house? And you could say, yeah, that looks good. And then I say, well, here's the hill that I'm going to put it on. And you say, well, you didn't say anything about the hill. That's completely a terrible house now. And, the context absolutely matters. And I think that sometimes we kind of, there's this kind of sort of maths envy that sometimes takes over people. And sometimes there's that idealism, because software does, as I said, there's these two different spaces, the sloppy human one that is filled with economics and ill-formed thoughts, and the fact that the realization that no matter what we do with any development process, people always talk about prioritizing requirements, stuff like that. Humans don't walk around with a list of priorities. That we don't actually, that's not a thing that happens in the brain. We don't have lists like that. And so my wife. I have. She's very organized. But I'm going to say that when people, but that's a thinking tool. A list becomes a thinking tool. When you provoke a human just randomly, they don't have they have to create a list. And it's going to be drawn from whatever is available. It's an availability bias there. Whatever is available at that particular point in time. And unless they've already really thought through, I'm going to use lists like this, unless they've actually structured that in there, then that's not naturally the way they think. Most people don't sit there thinking like, we want a product and I'm going to think in terms of these requirements. No, you're probably thinking in terms of other things that are your skill space. And so when we provoke humans into, I need a formal structure, give me a priority list, that's not how they actually think, but they can learn to move towards it. But that doesn't mean they're thinking genuinely like that. And then we have this associative mess, which is also where all the creativity comes from. And then we have this kind of like hard-edged stuff, which is very uncompromising. There's no negotiation with the compiler. It's not a matter of opinion whether or not this works or not. And then we're trying to do all of this. So we've got all these different strands of creativity, yet bounded by a particular formalism. And so it's kind of like you need lots of different points of view. And so although ultimately I believe that it is all underpinned by a perspective of engineering, in other words, and I think with software engineering, it's not, how do I put it? I did a talk a very long time ago at the GoTo conference. It was nearly 20 years ago, and it was an end note. And it was, it was the Gyro conference at that time. They hadn't called themselves GoTo yet. And it was entitled Beyond Metaphor, where I looked at a bunch of metaphors that we use in software development. And the whole value of them, I sort of said, it gives you different points of view. But I said, one of them is, actually what we do is engineering, but it's not engineering that has to worry mostly about physics and logistics. We don't really worry about logistics. It turns out that what happened, what does engineering look like when you take all of that away? And you're still making trade-offs and you're still doing a whole lot of things. It's just that you don't have to worry about the bridge materials. You don't have to worry about, all the materials that you don't have to worry about it the same way. There's a whole load of other things that just disappear, but that doesn't stop it from being a discipline that is learning based, that is in some sense pragmatic, but is also very trade-offs driven. That's a really, really important part. Mathematically, we know when people talk about maths, is the trade-offs are not quite there in the same way. When somebody comes up with a proof and they can't quite prove it, it's like, well, close enough. No, that does not pass the mathematical test. It's like Fermat's last theorem, which is kind of fresh in my mind because I interviewed Simon Singh a few months ago on some of his things, and he wrote a wonderful book on Fermat's last theorem, the history of that, and Andrew Wiles's proof. Now, everybody kind of suspected. Now, an engineer would have said, yeah, you know what, Fermat's right. It's close enough. We can't find anything that's good enough. We can't find an N for, there is, other than Pythagoras, other than a squared plus b squared equals c squared for a, b, and c being integers, you're not going to find any other powers. There is no n that is going to fit that. An engineer would have given up a long time ago. They would have moved on to the next problem because they said, actually, we've done a plausibility analysis and really it doesn't look like there's anything there. And given the time and effort, this is good enough. And that's in other words, there's a stopping point and a trade-off discussion that happens there.
Yes, it's Glenn Vanderberg did a great talk about software engineering a few years ago, and he says engineering in other disciplines, engineering is just the stuff that works, and that's it. It's that mix between adopting a scientific style of rational thinking to solve the problems where that's practical, but it doesn't have to be definitive. There's also this empirical little add-on that that's good enough. It's and that seems important to me as part of the discipline, is to not expect kind of quantum physics levels of precision in engineering, unless you're building something that's using quantum physics. You don't expect it. You don't do that if you're building a car. You're more pragmatic than that. And I think that's one of it's interesting that the way that you kind of couch that in talking about your talk is that it's engineering without those kind of the logistics. I talk about it in terms of, I think our mistake is assuming that engineering, because it's so popular in the real world, is production engineering that we're talking about. So, that they are a synonym, and they're not. There's also design engineering, which I think is much closer to what it is that we do. We're much less interested in the logistics of production because production's free for us. So,
yes. Yeah, I think that is a really important distinction, because it's one of those things when you zoom in, and I think as you start zooming in, you start realizing distinctions that are not necessarily, and I think that's both the strength and the weakness of any word. When we throw a word out there to say this is like this or this is this, we probably have a fairly clear idea in our heads based on whatever our experience is, but we've got no guarantee that the other person, the receiver, has the same mental model. And and that I think is a really important one. And it's sometimes when you kind of like push the edges of those definitions. So I think for me, one of the really interesting ones, actually, funny enough, and I wonder whether and this is tied. I know this is just like I can't tell you, but basically the late 90s, I read To Engineer is Human by Henry Petrosky. Wonderful book. Now, he's a civil engineer and a historian, and really wonderful book, but the subtitle is The Role of Failure in Successful Engineering. And it's that idea of understanding things through failure, which I wonder if that ties into me and my fascination with I'm going to take pictures and how other people send me pictures of failure. But that idea that actually we can learn a lot by nudging a system beyond what we actually understood, nudging it beyond our preconceptions, revealing our own assumptions. It's just like and occasionally doing that on purpose. One of the things I'm currently obsessed watching SpaceX build their starships in Texas,
and I've been following it for a while now. A little while ago, they decided that they made an unusual decision of building their spaceships out of stainless steel rather than aluminium, which is what spaceships were. Originally, they thought they were going to do it with carbon fiber. Then they looked at the alternatives. They came up with stainless steel because it got a better temperature range and for strength to weight ratio and all that kind of stuff. But at one point, they'd built these things. They'd flown some of them. They decided they were going to move from 4mm stainless steel to 3mm stainless steel. Same stuff, same type of steel, but just the thickness changed. You'd think that'd be the kind of thing that you could just, do your slide rule in the olden days, but run it through a computer and understand. But no, they built the system, and they pressure tested it to destruction to see how their welds held up, how their design stood up under that real empirical load in lifelike circumstances. See what happens at the point when it screws up. And that's what real world engineering looks like, it seems to me.
But there's that idea of like, we're going to do this and try this thing out and then see what happens. And for me, that's this idea that time is a really important ingredient of what we do, which I think is really missing from a lot of formalisms of what is software. It's the timeful aspect, not the timeless aspect, but the timeful aspect. In other words, honestly, I couldn't tell you the answer to this until I built it and we've seen it for a bit. I know it's not quite right, but it's plausibly in the right space. But I don't know what my assumptions are, and by definition, you don't know what your assumptions are, because I always like to point out that assumptions are really weird pieces of knowledge. They are only ever discovered. They are normally only discovered in contradiction. Somebody says something, you go, oh, but I had assumed that. At that moment, you discover you had an assumption. You've had it for a long time, but if anybody had asked you prior to that, what are your assumptions? You'd have said, I have none. Only when it is contradicted, you go, oh, that's an assumption. So it's just very curious from an epistemological point of view. This is really weird kind of thing. And it's the fact that it's kind of Lego bricks in the dark. There is a dark room. I know there are Lego bricks on the floor. The problem is, although I know that I have assumptions, although I know there are Lego bricks, I can't tell you where they are until I've stepped on them. I have assumptions, but I'm not going to do that by just standing at the door. I have to walk into the room. I have to tread through and say, there's one, there's another one, there's another one. It's one of those things. You have to be deliberate about this. You've got to put that stuff out there. And of course, prior knowledge can give you a real leg up. That's the standing on shoulders of giants. That's the cumulative experience. Like, why is it that we are recreating the errors that previous projects have done? We got all this experience, and we see this repeatedly at the level of individuals, companies, and discipline as a whole. It's a case of one of those interesting things is like, we all make mistakes. That's absolutely fine. We are always operating with incomplete knowledge. By definition, we're operating with incomplete knowledge. Software, as you said, production is free. That was a solved problem. 1950s. We basically solved the elements of that, and we've just been getting better at it ever since. But that whole idea of that leaves us with the hard problem of, and what is it we're trying to build and why? And how do we do that?
Yes.
Which turns out to be surprisingly challenging, but is by definition open-ended, because we're not producing identical artifacts. Here I've got, I don't know how many of these pens lying around my office, and they are all equivalent to one another. They are all, except for the ink content, substitutable for one another. They are identical. That's because they have a production. They have a production process that is designed to eliminate variation. We've done that far.
Software is never like that.
The software challenge is that if somebody comes along and says, I want that system over there running over here, well, that's a solved problem. If I see one of my sons, if they show me an app on the phone, I don't have to say, I need to build that. It's just like, I'm going to go to the store and get it for myself. It's downloadable. If somebody shows me a piece of code and say, that's really good, we now need to write that code over here. No, it's just a case of we've solved all of these issues, but we're left with that we're left with the challenging issue, which is not the production of the elimination of variation, but the production of variation. That's our job. When somebody says, yes, I want this system, but I want it slightly different. I want to, I want that thing our competitor has done. Well, that's different because we don't have their code. That for us, this is new. It's new to us. I want the old version. I want a new version of the system. So whenever anybody asks for a feature extension, they're not just asking for a feature extension. They're actually asking for a new system. It's the old system plus some new behavior. That's a new system by definition.
And that's one of the key facets of doing a good job, is to be able to make that move from the previous version to the new version easy.
Yes.
So I am increasingly of the mind that if you can't change your software, then the software is low quality. That is the practical, pragmatic realization of quality in your software. I don't care about anything else. I don't care what language it's in. I don't care what, if I can change it easily and safely, then it's good quality.
Yeah.
And pretty much, and there were some of these sort of deep tools that, things like modularity, cohesion, separation of concerns, encapsulation, abstraction, those sorts of coupling, those sorts of tools that allow us the freedom to make those kinds of moves when we realize, oh shit, we got it wrong.
Yeah, the freedom
we can make the change.
And I think that's really important, because I think for me, one of those insights, or an emerging wave of insights over the years, has come from this idea, okay, we're always operating with incomplete knowledge. So that means that whatever I'm building is in some sense wrong, although I think wrong is sometimes there's too much attached to that word.
Your best guess so far.
It's my best, based on what I knew. It's we did our best job. This is what we've got, but now we've learned something from it, either because the world told us or because we learned as a result, our own awareness of this. But what's interesting is you can derive a lot of the ideas that we value, modularity, loose coupling, and all the rest of it, from an understanding of how would you build something if you didn't know everything?
Yes.
Well, here's the thing I'm not sure about. Here's the thing I'm very sure about. This thing I'm not sure about, I'm going to really ram it in there and couple tightly to it. No, you want to loosely couple to it, because this is probably going to change. Yeah, exactly. I'm going to isolate myself from that. I'm not totally sure about it. I've kind of got an idea, but I want to put a little bit of distance between this, and that distance is our dependencies. That distance is our interfaces. That distance is, the idea is that all of this falls out naturally when you start saying, well, you can actually, and this is, I think, is fascinating, because it runs along kind of an alternative axis. Sometimes they arrive at the same conclusion, but sometimes they don't, to the traditional language of abstraction and things like that. Mm-hmm. How would you modularize? Modularize according to abstraction. Well, there's multiple ways of abstraction. We have different paradigms for that. Mm-hmm. But what is interesting is going, well, how sure are you about this? And it's just like, well, I'm not, I'm pretty sure we've done something almost identical. It's not identical, but it's almost identical. Well, that gives us maybe high confidence, and this worked out well. That's the second bit. People normally forget that. Doing it, sometimes we get stuck in a rut. It's just like, we did this before, and how did that work out for you? Yeah, not very well, but we're going to do it again this way. It's just that, no. There's an opportunity here. And that's that idea of, it's good to have a few ideas that you can trade off against one another.
Yes.
But then you've got that other idea of saying, well, let's go through this in terms of certainty. And I've done this a couple of times with people, and they're always kind of slightly freaked out, because you kind of come up with a rough kind of sketch of what you're going to do, and say, well, hang on, but we haven't actually talked about all of the design detail that they normally talk about. It's just like, well, what we did is we've just drawn a bunch of boxes and lines and things based on your confidence. In other words, when I've asked a question and you've said, oh, yeah, we're not really sure how we're going to do that. Right, I've drawn a line. There's a boundary there of knowledge, because we're sure about one side, but we're not sure about the other. I don't care what it is. I don't care what paradigm we're talking. There's clearly something we're not sure about. So maybe we shouldn't hug it too closely. A little bit of looseness. A little bit of a wall would
be good.
Yeah. And likewise, when somebody says, oh, yeah, we're going to do it this way, and a colleague says, oh, I thought we were going to do it this way. You know what? There's a line there as well, because there's clearly, this is not settled. And it may turn out that one of them is right one year and the other one is right the next year. In other words, things may change, whether it's performance characteristics or whatever, that favor one and then the other. And again, that's the timeful rather than timeless quality. But that idea there that we can get a heads up just by actually almost constructively using our uncertainty as a positive aspect to sort of see, well, how does this work? And then we've got the empirical side of things, which is, okay, here's what kept changing every release. What were the hotspots? What did we keep going back and saying, oh no, this time it'll be right. We'll just add this here. And that kind of, I think one of the first times I ever really noticed that question of stability properly feeding back was a Java system. It was a company that was doing a Java system, and they had the debate about, they were having the debate and have not yet resolved it, about checked exceptions. And for those tuning in who are not aware of this feature in Java, checked exceptions basically allow you to make exceptions part of the signature of a method, a sort of checkable aspect of the signature. And it's one of those things that in theory is a good idea, but that actually turns out that in practice, if you don't know exactly what you're doing, in other words, if you don't have perfect knowledge, and you're building a large system, they have a really nasty impact because they introduce an element that is unstable, or rather needs to be stable, but is not yet stable. In other words, how does this fail? I don't know yet, because we haven't fully understood this. It goes right back to where we started. What are the failure modes of this? Yeah. Short of saying something trivial like there is an error, and that's often what these checked exceptions tend towards, which is throws framework error. In other words, actually that's of almost no use to anybody whatsoever. Bad things may happen. Well, we knew that because because bad things may happen. You end up either saying nothing at all, or you say it so precisely that unless you've actually had this out in the field for a long time and converged on that, the chances are somebody's going to come up with a new failure mode. And it's just like, oh, well, so the curious thing is what you've done is that your happy day scenario, what you want from the method, why the reason you called it, you don't call I'm not calling this method, except perhaps in a test. I'm not calling this method in order for it to fail. That's not my goal here. I'm calling this because I wanted a result. I'm expecting that it's all going to work out. Yeah. So therefore, right at the edge of my vision and edge of my awareness is all of these failures, all of these possible failures, which we've not yet explored. And as time goes by, we get more refined understanding. Oh, this could be distributed. Oh, well, our distributed bit throws different exceptions to the ones that are those. So we've now made this thing which was local. Now it's okay. So we're going to have to change the signature again. So we've suddenly made something. We've caused churn in the interface. And this is one of those interesting things that comes out of the kind of the more empirical side of things. It's not that nobody who put that feature in Java did so maliciously or without thought. I certainly, I certainly, my understanding at the time and everything being up was like, no, there's some good thinking, solid thinking that goes right back to the 1970s in exploring all of this. But it's the scale. What happens when you actually create open systems that are large and with all manner of developers? It suddenly turns out, there's a fundamental problem here, and it's to do with rate of change and stability of knowledge, what we do and don't know. And that was a revelation. Anyway, for this team, it was a real revelation because they were split down the middle. Half were pro, half were anti, and I was just I can't come in and just sort of say, it's going to go this way or that way. So actually came up with an empirical approach, and I basically said, don't make anything checked. Look at, before you decide to make something checked, as it were, and seal it in, look at how it's behaved over the last few iterations.
Write a test to simulate the failures as well.
Not just, but the failures, do all of those. And they were actually quite good at that. But your understanding of the failures is the real thing.
How you respond to it, absolutely.
Yeah, and it turns out that some of these kept changing on a frequent basis. And I said, look, that idea is not yet stabilized. That idea is still young. Don't nail it in place. And which is a polite way of saying, like, actually probably, so in other words, don't make it checked until you're sure, which is a fancy way of saying don't make it checked, because the chances are they weren't going to go back and review stuff. But what we had is at least a maturity model. And it's this idea of that it doesn't matter what you think today, you're going to overvalue your confidence. And so it's this idea that time will give you the answer. I can't tell you how this is going to evolve. I can't tell you how other, and this goes across APIs. It's not just about failure modes. How this is going to evolve. How's it going to be used? What are the things that are frequently going to change? And then going back to your point about what we want to do is align the structures of our software with what are the frequent changes we actually experience, as opposed to people often pad their design or add complexity because they're saying, oh, well, maybe this will change. It turns out that the better your imagination, the worse this gets. So if you are a creative and imaginative developer, you can imagine all kinds of possibilities and the gold plating and the extra hooks and bits and pieces. And so the more imagination, the less imagination you have, the quicker you'll get the job done. The more imagination you have is actually, in that sense, it works against you, because you think, well, what about this? What about all of these are possible, but most of them are not likely. And probably what you want to do is see, well, what actually happens with this? And that gets you to ask the more meaningful questions like, well, should we release this API yet? Or should we release it and put a caution on it? It's just like, okay, this is a beta release. We're not planning to support this. This is a beta release. This is for you to try. In other words, it makes us a little more aware. It makes us look up from the keyboard and go, how are people going to use this?
That gets to one of the things that I think is really important, is just in software development is always thinking in that broader context of, how do people consume this, whether it's other developers or whether it's end users. How do people consume it's that stuff that you were talking about earlier, about the interaction between the relatively rigid forms of software and the relatively fuzzy forms of people. But ultimately always comes down to that, whether it's an API or some complex system that people interact with. It's so much about being pragmatic and learning that. And it's one of the things that drives me nuts working with big organizations when they, silo up the development process to the extent where you get development teams who have no idea the context in which their pieces of software are used. They have some kind of people giving them requirements in the form of programming by remote control, which they're supposed to build out, churn out these widgets, and they don't have any context. And you get to use software that you can tell sometimes just by using the software, nobody's ever thought about actually using this bloody piece of software. It's so bad.
And that idea of usability, it's a turtles all the way down. It's kind of like you have the end user, but then also as software developers, we are clients of our own products. We are clients. You're creating. It's the classic kind of consumer and supplier metaphor for understanding components and interfaces and so on. That how is somebody going to consume this? But also there's that contractual idea of like, and what am I going to say about how they should use it? Because everything has a boundary, everything has a limit, and it's that idea, because the over engineering issue. I've seen that where, in fact, again, I can pick on Java, but I've seen it certainly in other cases. So when Java arrived, it basically said, hey, everything is synchronizable, so you can make it thread safe. And I remember thinking at the time, that's a really bad idea. That's a terrible idea. That's not how you do this. Because I remember at the time, somebody sort of showed me some C++ and said, oh, this isn't thread safe. And I said, no, it's perfectly thread safe. You can pass one thread through it. That's it. Threads say, if you do anything else, on your head be it. But I've just told you the circumstances under which this will work. I have given you a context under which this will work. And that's not me being picky. It's actually a genuine answer, because otherwise people do go around and they start gold plating everything, and they do so very badly. And it's just like, no, I don't actually. The question is, this is thread safe. Oh yeah, but you can't share it between threads. No, I didn't say you could. It's perfectly thread safe. I can run it in one thread on its own, and that is its safety level. Whereas there are some code that has a safety level of 0. In other words, this is thread safe if you pass 0 threads through it. It's buggy.
I can give you a real world example of that. The danger of synchronization blocks in Java. Martin Thompson, my friend, years ago worked on. At the time, we thought it was the first ever internet bank. So he was called in to consult on this because they had a serious performance problem with their Java implementation. It was one of the early big Java implementations in the sort of mid to late 90s. And he went in, and several people had been to look at that, and it turned out, to cut a long story short, that that they all of the tests ran and it all looked fine. They put it into production and the performance absolutely tanked. And it turned out somebody put a synchronization block around some piece of code in the critical path, so this internet bank could support one concurrent user, and everybody else queued up So,
yeah. and that's the thing, is that for people answer, oh yeah, but this needs to be thread safe. Well, what do you mean by that term?
Yeah.
And it's like, why are you doing, there was again the context. So it's a case of like, not everything wants to be shared between threads, and there are other ways. And everybody was a lot happy in the 90s, and finally got, it's one of the reasons I keep certain old books around, is that you can kind of see the shifts in style and approach. But I also remember with the client, this was a C++ system that we went through and looked at their problem, and they just sort of, they weren't highlighting a performance problem, but I remember looking through, they've got this huge stuff in memory, lots of data, lots of rows of data in memory, and there's 30,000 locks. And I'm sitting there going like, I'm pretty sure this is all the ways that you could do this. This is probably not the right way. And it was one of those kind of like, take a step back and look at it and go like, well, actually what you've got, you've done it as a kind of a data-centered problem with lots of threads operating on the data. And I said, but if you understand what the threads do, I said, they actually follow a life cycle. And that life cycle, we could do that as a data flow. In other words, it worked out, basically, it was a data flow. We basically, you don't need anywhere near as many threads. You're stealing from yourself, it turns out, with a lot of this. And it turns out if you do it as a pipeline, then we ended up with only needing 6 locks, and that was in the bits that connected, that was in the pipes. And in other words, the point is the data, but they said, but the data itself is not thread safe. And I said, yes, it is, because its environment guarantees that it's thread safe.
Yes.
That data will only ever be accessed by 0 or 1 threads at any one particular point in time. And that's the game. And when we start looking at this, and again, this is this engineering to context idea. It's when we talk about car safety and road safety and all the rest of it, we understand that there are conventions, rules of the road, and contexts in which we evaluate that, and that outside of that there's no guarantee. And that's, again, for me, that light bulb moment I had when reading in the early days of patterns, actually reading outside the kind of the software space, going like, right, there's this idea of context. Where does this idea apply? Beyond which we make no guarantees. And that doesn't mean that it's a bad solution. It just means that it is no longer appropriate or, outside that context. It's a perfectly fine solution for the thing that it was intended for. And that, I think, rubs up against a different trend that sometimes we see developers, architects, and so on, is overgeneralization. The idea that everything must be general.
I think that one of the traps of our disciplines that seems to me inherent in the nature of software is that we're often inches away from some quite deeply complicated problems. Whatever the level of abstraction that we're working at, almost as soon as you have it seems to me fundamental that as soon as you have two copies of information in separate places that are changing independently, you've got a world-class, first-class quantum physics level problem. This is hard stuff. However, whatever the nature of the information, however it is that you deal with it, working on high performance systems along with Martin, building exchanges and trading systems and stuff. We measured the costs of concurrency, locks, compare and swap operations in processes and all those kinds of things to try and optimize the performance of our systems. And that, one of the things that I've observed is that the more that people know about building concurrent systems, the more their advice is don't do it unless you can possibly avoid it.
Yes.
This is incredibly difficult stuff. So things like adding synchronization blocks and saying everybody can now in Java can write threads, or having thousands of locks in your C++ program are all, seems to me, symptoms of not realizing that this is a point to stop and think hard, because this requires hard thinking. This is a difficult part. And it seems to me that concurrency and coupling are the kind of the really hard parts of our discipline.
I think so, because I think because again, coupling is, and what's interesting, actually, it's interesting you draw those two together, because I think the interesting about coupling is that concurrency is hard for us to reason about and conceptualize. coupling suffers a different problem, but interesting. But both of them, which I find fascinating, both of them manifest themselves physically. In terms of concurrency is about structuring things in time.
Yes.
But if somebody says, "Well, how tightly coupled is this code base?" I tell you what, let me do a build.
Yeah.
You can, in other words, you can actually measure the energy of a build, and it's one of those things that I remember turning up at a particular. It was an engineering project, electricity company. Multiple companies were subcontracting. It was a political nightmare. It was just pure Conway all the way through, but in the failure mode. And it was a political nightmare, and all kinds of fascinating things. But one of the most interesting things was, as a development team, the team that I was working with, what we were working on was very much back end stuff. It was much more towards the hardware. It was the real-time stuff, but it was kind of like we felt like we came out of our cave to go and speak to these other people. It's just, oh my goodness, this is absolute enterprise chaos. And then what was funny is that because we were building for multiple environments, we were building for 32 and 64-bit environments. We were building for slow environments, as well as environments where we had high-powered CPUs, and as we had a framework that's supposed to work everywhere. But the embedded environment, oh my goodness, the builds on that were so incredibly slow that we cared about dependencies at such a level so that we had fast builds, which meant when we ran it on a 64-bit platform, it was practically instantaneous. It was a beautiful side effect. But then we encountered all these other people who were just doing all kinds of stuff with their code. And this was like, I'm going to call it C+, most of what they were writing, because it was clearly using a C++ compiler, but I don't think it got much beyond C. Yeah. But the way they managed their dependencies, or didn't, everything depended on everything else, and the build times were staggering and shocking. We ended up building an isolation layer between our company and the rest as a result, because it's just like we got so used to fast build times on these platforms. Yeah. And it's just that idea of like, I can, how good is your coupling? I can either measure it in joules or I can actually time it. You see, it's kind of like, our builds take a lot less time than your builds, because we've stripped it right down. What is essential? So there's a physical aspect there, but it's not, and again, concurrency is this physical one, but concurrency we find difficult to reason about, because having so many things in motion is not a strength of human beings, but coupling is more a sense of scale. Is once we've it's that idea of like, there's a large system is like really understanding what a tangle looks like, really understanding that this dependency means that, and they are both limits. We are limited by what goes on up here, but in slightly different ways with those two. But I think you're right that they are fundamental. They remind us of some of the physics that we do encounter in the universe. And coupling, certainly entropy in the build, but concurrency is that point where your idealization lands in the real world, and sometimes it reveals assumptions. I've certainly had that with one client. I remember one client, we did this kind of surgery style thing. I had a couple of days there. I ran some training, then I had a couple of days, and people would book a morning or an afternoon, and I'd go with the team. And I had one team say, "Oh, well, an hour of your time this morning would be great." And I said, "Well, no, you can have the full 3 hours." And they said, "No, we won't need that." They walked in, and I remember asking a particular question. I said, looking at the code they were going through, and I said, so how many threads run through this piece of code? Because I was aware they were using threading. How many threads run through this piece of code? And there are a number of correct answers to this. 0 is a valid answer, which means this code is dead. 1 is also a valid answer, and many is also a valid answer. I didn't get that. What I got is usually 1. And I said, that's interesting. What do you mean by usually 1? Why would you not say that's many? As far as I'm concerned, that's many. Well, what we have is it's single threaded, except this is single threaded code, Kevlin. Except occasionally another thread will just sneak into this bit here. It's just like threads don't sneak. That's not how schedulers work. And they had this mental model of threading that was not actually how threading works. They had kind of thought that threading respected the natural boundaries of the language and statements and blocks and things like that. And they said, well, it only happens occasionally. I said, well, you only need to fail occasionally. I said there's a race condition waiting to happen here, because you load this and then you validate this here. What if something else sneaks in at this point and you've got an unvalidated bit? It's just like, and it's kind of like one person looked at another and said, that might explain this intermittent bug we've been having. And they said, what should we do? Should we add locks everywhere? And I said, no. Actually, what you need to do is take a step back here. The problem is not to add, but actually to sort of say, well, why are you doing this? What they were doing was a lazy load.
Yeah.
And it's a case of like, why are you doing the lazy load here? And they said, well, we don't know, the reasons are lost to time. But I said, because the problem goes away if you do an eager load. If you do an eager load before it goes multi-threaded, then the data you're looking at is actually immutable. It's reference data. Yeah. It's the load that is the state change. And I said, let's do the opposite way. Rather than add locks, let's take a step back. I mean, honestly, given enough time, I would have removed all the threads from this application. It was not a threaded application, but it was a case of, actually take the opposite view. This is a question of time. You're doing the load at the wrong time. You should be doing the load before you go multi-threaded. And if you do that, then the problem solves itself. But it's that shift in time and perspective. But my favorite bit, again, to do with time, was when the lead in the room said, we might need more than that 1 hour, Kevlin, now. Because when I said, do you have more code like this? It's just like, But again, it's because it's not, and it's not to criticize, because that's the whole point. It goes back to something I said earlier. We are always operating with incomplete knowledge, and we are filled with assumptions. Yeah. And until you've actually run into those, you don't realize what you're missing. And you don't realize the magnitude of either how well you've done something or actually how wrong you've understood something. It's like, oh, actually, no, I'm using completely the wrong mental model for thinking about this. And that mental model has informed how I've structured the software. The software is kind of like applied thought, and that mental model, it's off. And so that's the squishy human bit, that's the learning bit, but it's also the bit we need to sort of say, we need to have a bigger process that is tolerant of the fact that we are imperfect and that we can't know everything. And that's the whole point. This team had not really interacted with that and had not accommodated that idea at that level. And most teams, I don't think, have. I think it's a very difficult thing for us to do. It's almost against the culture and the nature of software development in many companies.
I think you're absolutely right. And forgive me bringing it back around to my stuff, but I think that's one of the things that treating this more like an engineering discipline ought to be able to give us is just those disciplines of just being able to just recognizing that we don't know the answers when we're starting out, recognizing that we're probably not going to be right, therefore working more experimentally, therefore working to control, manage the complexity of the systems that we build, and to measure things and to try stuff out and all of those sorts of things. And test-driven development is certainly part of that for me, deeply. But I think that mindset is so important. One of the other kind of deep properties, it seems to me, of software is that it's, unlike lots of other things, it's actually very easy to start. You can learn to write your first simple lines of code in a few minutes. If you've done a little bit of algebra, at least, it's trivial to just do your first easy, trivial bits of code. But it's deceptive because, you don't go very far before you get into some of these more complicated things that we've been talking about. And as you say, as soon as you start things like concurrency, that's really hard for the best people in the world. It's like, it's one of those things about Martin Thompson. They're world-class experts at some of this stuff, but they think really hard and worry about shared data at any point and all these kinds of things. So to be able to manage this sort of stuff, it's an interest. I think that's one of the beauties of it. It's a challenge of it that's delightful, but also very, very risky. I've been talking to a few people recently about low code solutions. And I think my take is that many of those sorts of systems suffer from that kind of failing because they assume that it's the typing of the code that's the hard part, where it's these broader design concepts and how we organize the information in ways that we can make a mistake and come back to it in future and correct it and identify the mistake.
That idea, the identification and the recognition of how things, as you say, it's deceptive. Things can get very messy very quickly, and we see that. So I've given a few, partly as a result of failure screens. I've given a few talks on software failures and the natures of failures and what contribute to them. But one area of enduring fascination for me is spreadsheets, which I find absolutely fascinating because it takes
Yes.
a good idea and implements it incredibly badly.
Yeah.
In the sense of vision, people find grid forms. It's very, very intuitive. There's, you know, I mean, what kid doesn't like squared paper? You know, this kind of stuff. It's like we like laying things out in grids and tables and all the rest of it. This is incredibly intuitive, and it's a very
to be fair, that might just be you and me.
That's true. Yeah, this might be a conversation just the two of us. Obviously, anybody else in the comments is free to add in, but you know, it's this whole thing of like is incredibly intuitive at that level. But the problem is there are two very fundamental issues that scupper spreadsheets and make them massively error prone. One is three. Let me raise that to three. Okay. One is the fact that you end up with a lot of interdependencies very quickly if you're doing anything that is reasonable. And then the next bit, and they're all invisible. Yes. This is the one this is the one thing that as a software developer you kind of look at a spreadsheet and go, well, that's a nice start, but where's the button that I press that shows me all the dependencies between everything? You've hidden all of the code. You've hidden the bit that actually makes it, that shows me the structure and therefore reveals my assumptions. You've actually, I understand.
And there's no real mechanism for me to step back to safety when I screw it up.
But there's that idea that we've lost the bit. In other words, what we've done is we've presented the veneer and treated that as the whole. Whereas no, software spreadsheets have a deep structure, but honestly, even just using something like even a Word document has better structuring tools than Excel. In Excel I can go in and I've got the grid. That's it. That I'm done. That is my abstraction. That's the level at which I'm invited to think. The code is fragmented and scattered around. The relationships are thrown to the winds. It's a matter of detective work and archaeology to recover them. Whereas when I work with a document, and this is true of many different editors and word processors, I can get a high level structure. I can do an outline structure. I can say, show me the dependencies, show me the cross references, do this kind of stuff. In other words, spreadsheets are absolutely, they are an absolute mess. And I always say this, and somebody says, oh, but users find them intuitive. They find them intuitive to use, but it's like walking to a minefield. You can walk into a minefield incredibly easily. The problem is we have been depriving, and I think this is, I'm going to push this one right back to the profession here. We've been depriving people of the things that we know. Because we know that a spreadsheet is it's got a terrible type system. It's astonishingly bad. And if anybody ever throws up the argument of backward compatibility, that is absolute nonsense. We've actually seen formats for documents change on a 5 to 10 year cycle. There's no backward compatibility issue here at all with things like Excel. That's a myth. You're looking at a 5-year window at most. Explain to me why it is that my Excel looks like it was developed 30 years ago, but everything else that I'm using looks like it was developed in at least the last decade. Why has Excel failed to take on board all of these other tools that we know to show dependencies? And the third thing to come back to is that people don't realize that there are these issues. So they scale up very, very poorly. They embed many mistakes. Now, the point here is the reason I'm riffing on this is because you talked about the low code stuff. Spreadsheets are by far and away the world's most successful low code to no code solution. And anybody who hopes to rival that is just kidding themselves. I'm going to say that right now. I'm not predicting the future. It's just like those hit a very particular stride. They have embedded themselves in a particular way, in a particular world, and they're very current. They are ubiquitous. But if anybody wants to learn how to do and how not to do, learn from its successes and learn from its failures, and what are the things that it's good at and not good at, and then also go back through the history of 4GLs, and what you'll discover is that there's a line that you're looking to draw. And you need to understand that it's not universal. There's a line here. You need to work out where it is. It's like, this is the bit that allows people the convenience they want. And then there's this other bit that's incredibly hard. If you're assuming that they can do, they're going to be in for a big and nasty shock. And we're just going to be throwing more stuff over the wall at other people we need to customize this, or, this is something that we knocked up. But we're having a couple of problems with it. And then kind of somebody looks at it and You know, it's just like at this point they suddenly discover that they are in fact an Olympic runner, because that's the only way they can get away from it fast enough. That we are, if we're not doing this one right. So I don't have any grievance with low code. It's just that when people talk about it as a general solution, no, what's valuable is a highly specific solution. That's its value.
That's the value. A narrow constrained focus.
Yeah.
They're
and
great
really
tools.
good at that thing. Again, it goes back to this question, this quest for generality that we sometimes have, and we overgeneralize, make things either we end up overgeneralizing, make things ridiculously complex for ourselves, or we end up not overgeneralizing and forever working around, taking something that really wasn't suited to that world.
But it's that really, you know, shades of grey kind of slippery slope over a snake pit. You're mixing my metaphors horribly, but you kind of go from, you know, I'm adding up a column of numbers in my spreadsheet. Cool, that's really nice. It's really good for that. To you know, I've built this thing, and if I change that, it goes and recalculates all of these other things and does all this, you know, which is an unmaintainable big ball of mud. And you know, there's no easy way to define the line between where you step over and it becomes don't do that, write that in code
with Lego bricks. Yeah,
it is. Absolutely.
You know, it's just like you tread carefully, push your foot out just in front of you, just to. And I think that is that feeds back into this idea that what we're looking for is an approach, a philosophical approach, but a practical approach. I mean, you know, I'm definitely of the school of thought that. I guess old school philosophy, in the sense that philosophy was intended to be a practical thing to help you understand life. It was not intended to be abstract and disconnected from life. It was intended to be quite the opposite. So for me, this idea of actually what we want from how we think about software, we need to understand is like, it's a bit experimental. There's things that are unknown, and actually not only is that okay, but that's actually part of the job. It's not just acceptable. It is the job.
It is the job. Yeah. So I've just become aware of the time. The amount of time
we were talking about time, and now we're aware of it.
It's been so much fun having the conversation. But let's try and round this off. So if you could. If you could summarize this, what do you think is the advice that we should give people to help walk this tightrope, explore, you know, walk into your room of Lego with bare feet?
Yeah. Well, I guess the simple one is run away. But that's the only. I think it's really to understand that what. The challenges that you are, the challenge and the joy. Let's. I think we're always putting up challenges. I think we need to accept that sometimes the challenge is the fun bit. You know, it has two aspects to it. The challenge and the fun is that you are working with incomplete knowledge. There is a joy to learning something, and there can also be a joy in discovering better solutions, alternative solutions, penny dropping moments where you go, you know what, I've been thinking about this wrong, and you know. Yes, I've over abstracted. This really is just a string. The abstractions I wanted to do are over here. Those
are the points that I love. Those are, oh shit, I was thinking of it wrong, and now I can see a new path. Those are the things.
It's a case of like, I've been devoting my effort to this, but actually the fun is over here. If I reframe the problem, in other words, it's that idea of take a step back. And I think a little bit. Something I keep meaning to do a talk called Slow Agile. I think I'm probably going to do it at some point. But it's this idea that although we often use the language of fast in connection with many of our practices, I think sometimes there's a different emphasis I might want to give, which is that some of what we're trying to do is to do things sooner as opposed to faster, which is not quite the same thing.
Yes, I use the phrase. I think that what you might be saying is the phrase that I use is small steps.
And small steps are a way of achieving, and it's this idea of, and I was just talking to a group today about refactoring. I was trying to emphasize to them, you know, in terms of all the design practices and so on, I said there's a difference between running and walking, and there's a very simple idea that running is defined by the fact that at various points you have 0 points of contact with the ground. You know, if you watch somebody running, it's 0 1 0 1. If you watch somebody walking, it's 1 2 1 2. There is always at least 1 point of contact with the ground, and there Now, what does this mean? It means you move from moment to moment more slowly, but you are also moving with more certainty and more assuredness, and the ability to change your direction. If you try changing your direction when you are running, or when you stumble when you're running, and I have relatively recent personal experience of this, and I can say it hurt an awful lot, and I was not able to walk for a few weeks. Whereas had I had that fall when I was walking, I'd have just got up and walked off. The point there is that software development is not a race. Although we use the language of fast, the timescales we're thinking of, sometimes it encourages the wrong behavior, I think.
Yes.
It's again one of those things when I use a word and somebody else picks up, oh, they're talking about raw speed. Actually, we're not trying to optimize for speed of development. There's other characters. What we observe is the speed of development, or is speed of deployment. But the thing, it's not the pedal to the metal. You're just going to exhaust all your developers and exhaust their capacity to think creatively. It's the idea that actually what we need to be doing is walking. It is the idea of stability. It's the idea of like, oh, that's not right. Let me just pull back a moment. It's the small steps. It's the let's roll back and take a different path. Whether that rollback is a version control rollback, whether that rollback is a conceptual rollback, whatever it means, it's the idea that we have given ourselves the opportunity to pay attention to what we're doing. When you are moving at high speed, you're not paying attention to your surroundings. All of this talk of feedback just disappears in the wind. The whole point is you are sensing your way, and that you're adjusting according to that, and it's your feet on the carpet type thing, it's the sensing your way. How are we doing? Is this that I originally intended this, but now I see this? Why? Because I've taken the time to do that. I'm not, individually as a human being, remember, it's all about people ultimately. For me to appreciate which formal approach I'm going to take, which structure, which choices, which modules I am going to select, or my criteria for modularity, which ones I'm going to do here as opposed to there. That's going to take a deliberation that doesn't happen when you're exhausted and running at speed. It's not a productivity conversation. So I think for me, most of the advice I give people is just like, honestly, go a little bit slower because you'll go faster. It's one of those.
That's great. No, that absolutely. I hadn't thought of it in those words, which is always interesting, and always an interesting thing, but still was still reinforcing my prejudices. So good both ways around. You gave me some new things to think about, and reinforced my prejudices, which is great. I've really enjoyed the talk today. Thank you so much for taking.
Thank you, Dave.
It was great. It was a fun exploration. Please do check out Kevlin. Check his Google unique name. You'll find his stuff, and lots of good books that Kevlin's written as well. So thanks, Kevlin, very much indeed. And I'll let you know when the video is available. Thank you.
Yeah, thank you very much, Dave. That's perfect.